Let's take a look again at integration by substitution. So it's based on the chain rule from differential calculus. If we have an integral of a function that's a composition of functions, and we have the complete result of the chain rule here, so the derivative of the inner function lives here also, then we can take the derivative. So trick is we do a change of variables. We pick this new variable, let's call it u. U we let be the inner function. Then du would be the derivative of g of x, so it's g prime, and then writing it in differential form, we throw the dx over onto the right. So substituting here, we replace g of x with u, and du is equal to this whole part right here. And so now it's much easier, we just have to find an antiderivative for f of u. And then there's a couple of ways to proceed from there. So let's do a couple of examples. So here I have the sine of x squared times 2x. And so my hope is that if I let u equal x squared, I'll be able to build or discover du. So du would be 2x dx. And I happen to have exactly 2x dx here, so I don't have to fiddle with anything. So there's my du, and here is my u. So I can rewrite this equal to the integral of the sine of u, u. Now, antiderivative for the sine would be the cosine. U, slight catch, is it's got to be a negative, right? Because when we take the derivative of the cosine, we get the negative sign. That negative is missing. And then we're going to have some constant. We don't know what it is because we don't know the bounds of integration here. To get the final answer, we have to reverse substitute. So we replace u with what it's equal to up here. So here, bring that back in, we get the cosine of x squared. And the constants still hang around. So this cosine, negative cosine of x squared plus c is a general antiderivative for the sine of x squared times 2x. Now, substitution doesn't always work. So for example, if I had the integral of, say, the cosine of x squared dx, I would try u equals x squared, in which case, like before, du would be 2x dx. And problem here is there's no 2x, so perhaps I could do something like move the 2x to the other side. So I would get over 2x u equals dx. But now I have a problem in that I've mixed variables. So for example, if I go to apply this substitution, I would get cosine of u, and I have dx would be 1 over 2x u. Now this is a problem because x is a function of u, and u is a function of x, and then this is just a mess. So maybe I try to get rid of the x. So if we come up here, you might note that you could solve that for x, and that would be plus or minus the square root of u. Plus or minus is a problem, so maybe you would ignore the plus. So now I have cosine of u times 1 over twice the square root of u. And even ignoring the minus here, I'm still worse off than I was before, in a sense. I traded the x squared for 1 over 2u on the outside, and this is more complicated than it was before. So here, integration by substitution was a failure. And now I need to do something else. So I'm not going to do something else there. I'm just going to move on. It's about substitution. So let's try, oops. There we go, substitution. This is an awesome problem right here. So tangent of x. So thinking back, what function had a derivative of tangent of x that we dealt with before? And it turns out none of the functions you dealt with before in Calc 1 had a derivative of just the tangent. So we need to try a new trick. Well, a trick we've tried before would be to rewrite the tangent as sine of a cosine. And at first glance, that looks worse than what I started with. And in some sense it is. It uses a lot more ink. However, this sets me up to use a substitution. So the substitution I'm going to choose here is to let u equal the cosine of x. And then du would be the sine of x dx. So coming back over here, rewriting that, I now have a fraction still. Now here I almost have my du, so if I just bring that negative over to the other side, then I'm going to have -1 du, and then the cosine is just u that sits in the bottom. That's a little bit better here. I could pull that -1 out, and 1 over u to u has an antiderivative of the natural log. So then I get -1 times the natural log of the absolute value of u plus c. And then I can substitute back in. This gives me -1 times natural log of the absolute value of the cosine of x plus c. So now I have an antiderivative for the tangent. We could tweak this a little bit. So for example, other versions of this, a negative multiple of a logarithm comes in as a power. So this could be written as the natural log, the absolute value of cosine of x, power -1. Now that's not the inverse function, that means flip the base. So that's going to give me natural log of 1 over cosine of x plus c. And you might remember that the reciprocal of the cosine is the secant. So then, I could say another derivative or antiderivative would be the natural log of the secant of x. And to make it general, we add that constant. So often in integral tables or integral software, we'll use the natural log of the secant of x, but it could be the opposite of the natural log of cosine of x with that antiderivative. Functions can have many antiderivatives because of that arbitrary constant there. All right, cool. That was powerful and beautiful. Let's try another. So here I have a relatively complicated function. So generally, u is the inner function. So I'm just going to rewrite this first. I'm going to say this is the integral of 5 over 1 plus. I'm going to note that 25 is a perfect square. So I'm going to write this as 5x squared dx. And the reason I'm doing that is because this one right here to me looks like the derivative of the arctangent. So remember, the derivative with respect to x, the arctangent of x, 1 over 1 plus x squared. And I almost have that there. So this is where I'm going to use my u substitution. So I'm going to let u equal that 5x, and then du would just be 5 dx. And I have that right here. Here's my du. Here, I guess. So here, my inner function, I'm going to choose the u is 4x plus 1. And that means du is 4 dx. And I have that right here if I view the 16 as 4 times 4. So then there's my du. So I'm going to rewrite this as the integral of 4 times u cubed u. Next thing are the bounds of integration. So I'm going to rewrite those too. So making a little table on the side here for x versus u, if x is -0.5, then half of 4 is 2, make it negative, -2 plus 1, u would be -1. And then if x is 1, u would be 4 plus 1 or 5. I'm going to rewrite these boundaries and make a note that I did so by saying u is now going from -1 to 5. Otherwise, we have to back substitute and bring the remaining back. This way I don't have to worry about the back substitution. So antiderivative here would be 4 times u raised to the fourth divided by 4. Well, that's nice. The 4 would cancel for us. And then I just have to evaluate this from 5 to -1, -1 to 5. So that's going to be 5 to the 4th power minus -1 to the 4th power. Parentheses are important. So, sorry, my pen is leaving trails. Let's see, what the heck is 5 to the 4th power? I do not know that one off the top of my head. Calculator. Five raised to the 4th is 625. So then here we have 625 minus 1, which is 624. That value raised to. All right, one more. More written. There we go. So this one's a little tricky. What we're going to do is, so we have a problem right now. We have a square root, x plus 1. We have the x on the outside. We don't have an easy way to find an antiderivative at the moment. So we're going to do substitution and do some algebra. So here I'm going to let u equal x plus 1. And du then would be just dx. So the problem here is this x on the outside. So I'm also going to have to take this expression and solve for x. So x would be equal to u minus 1. I want to replace all the u's with x's. I tried this on an earlier problem and failed. So the 2 is just hanging out. I'm going to bring that outside. X is now going to be u minus 1. It's got to be in parentheses. And then the square root of x plus 1 is now the square root of u. And then du is just dx. Nice thing about this right here is I can then distribute the square root through here. So I took the plus, this addition out here, and rewrote it as a subtraction outside, which is beneficial because I cannot easily bring the x inside here. So then this becomes twice the integral of u times the square root of u minus the square root of u. And then we can use our exponential rules to clean that up, and then it's not so bad. So this would be u to the first times u to the 1/2, which would be u to the 3/2 minus u to the 1/2. And you guys are awesome at using the power rule, so I'm going to let you finish this. So fun with substitution, do good math, have fun. Let me know if you have any questions. Bye.